Good afternoon. So the last time we have studied classifying particles, so we'll continue from the same topic. So let's continue. So we have seen that we have 6 main quarks, 6 types of quarks. And we also said that we just need to learn 3 of them: up quark, down quark, and strange quark. We said it. And if you look at these quarks, the up quark, it will have a symbol of U and charge +2/3. Down quark, the symbol D, the charge is going to be -1/3. And strange quark, the symbol is going to be S, and the charge is going to be -1/3. So we have seen these quarks and antiquarks last lesson. So now we will start from hadrons. Hadrons affected by the strong nuclear force. So we have to keep in our mind that if there is any question related to hadrons, we should know that hadrons are affected by strong nuclear force. And we have 2 main hadrons. These are very important, and we will see lots of questions related to these type of hadrons. The first one is proton. The proton is a kind of hadron. Okay, and the proton is made up of up, and down quarks. So when we have proton, it consists of up, and down quarks. If we look at the charges of these 3 quarks, we know that up quark has a charge of 2/3, +2/3. The another one, we have also 2/3, up quark, and down quark has a charge of -1/3. So if we add all of these 3, it's going to give us what? It's going to give us the +1. So that means it's the charge of proton. We know that proton is equal to what? The +1 charge. And we know that the charge of one proton equals 1.6 times 10 to the power of -19 coulomb. It's a charge of 1 proton. And same thing for neutron. So let's take neutron. The neutron is made of up, down, and down quarks. Up, down, and down quarks. Again, if you look at the charges, the charge of up quark is +3. The charge of down quark is -1/3. And we have another down quark. Also, it's going to be another -1/3. If we add all these 3, it's going to be 0, which is what? Which is the charge of neutron. So we know that the neutron is neutral. So that means the overall charge is going to be equal to 0. So we have to keep in mind that the protons and neutrons are hadrons. And we have to memorize the protons consist of 3 quarks, which are up, and down quark. And the neutrons consist of up, down, and down quark. So we have to learn and memorize these quarks for proton and neutron. So let's continue. So the next one is going to be neutrino. So the neutrinos are fundamental leptons. Okay. So these particles are classified as leptons. They do not have any charge, so no charge, almost no mass, rarely interact with matter, maybe passing straight through us and Earth, predict to explain the beta decay conservation laws. And we have 3 types of neutrinos we will deal with. The first one is electron neutrino, and the symbol will be VE. Muon neutrino, the symbol will be VM, and tau neutrino, the symbol is going to be VT. So if you look at the symbols, all these 3 neutrinos start with what? They start with V. So VE, VM, and VT. Electron neutrino, muon neutrino, and tau neutrino. These are the fundamental leptons. So can we explain beta decay in terms of quarks? So let's look at beta decay. But before that, we should know that when we have any radioactive element, radioactive material, we will have three different radiation. And these radiations are called alpha, beta, and gamma. Before looking at beta decay in terms of quarks, so let's see the properties of these three radiations, alpha, beta, and gamma. These are very important. And first we will look at these three types of radiations. Okay, we have three types of radiation, alpha, beta, and gamma. So we should be also able to define the symbol of these three different radiations, alpha, beta, and gamma. Now let's look at the properties of these radiations. The first we will start with alpha. The alpha particle is basically a helium nucleus. So what does mean helium nucleus? We know that in helium nucleus, what we have 2 protons and 2 neutrons. So in helium nucleus, we have 2 protons and 2 neutrons. So that means alpha particle basically equal to the helium nucleus, helium. And in helium, what we have 2 protons, 2 neutrons, and the mass number will be 4. And we will symbolize the alpha particle by like this. And we always write the proton number here, 2, and the mass number here, 4. Don't worry about the number of neutrons. We will not show the number of neutrons for alpha particles. So we have to define alpha particle like this. Alpha, the number of protons is 2, the number of neutrons 2, the mass number is 4. And the alpha particles have a relative charge of +2 because what? We said the alpha particles equal to the helium nucleus. So we know that in nucleus, which particles we have? In nucleus, we have only protons and neutrons. And we know that the neutrons are neutral, no charge, and the protons are what? Positively charged. So that's why we said we have 2 protons for alpha particle. That means a relative charge of +2. Alpha particles have a high mass compared with beta particles. The mass of alpha particles are higher than the mass of beta particles and speed up to 0.1 times the speed of light. And we know that speed of light is equal to 3 times 10 to the power of 8 meters per second. So the speed of alpha particles is what? 0.1 times, so 0.1 times 3 times 10 to the power of 8. So which is equal to, it will be 0.1 is going to be 10 to the power of -1, 10 to the power of -1 times 10 to the power of 8. So 8 minus 1, it will be 10 to the power of 7. So the answer will be 3 times 10 to the power of 7 meters per second. So these are what? These are the speed of alpha particles. And alpha particles have very strong ionizing effect. So what does mean ionizing effect? So that means when the alpha particles collide with any atom on their way, they will be able to easily remove the electrons from that atom. And we call that one ionizing effect. So the alpha particles have very strong ionizing effect. They can easily remove electrons from the atoms that they collide. And the next property for alpha particles, not very penetrating. So stopped by paper or skin or a few centimeters of air. So they're not going to be able to penetrate through the materials. It can be easily stopped by paper. And the next one is deflected by magnetic and electric fields. Because it has a relative charge of +2, that means positively charged, they can be deflected in magnetic fields and electric fields. And we will see how they will be reflected in these fields. So these are the properties of alpha particles. And the most important properties of alpha particles are, the first one is very important. The alpha particles are equal to what? A helium nucleus. That means they have 2 protons and 2 neutrons. And they have very strong ionizing effect. And they are not very penetrating and deflected by magnetic and electric fields. These 4 properties are very important, and it's very likely to see these properties in questions. Now let's move to the beta particles. Now we will see the properties of beta particles. So let's see the properties of beta particles. Yeah, now the beta particle. Each beta particle is an electron. So we can basically say that an electron is equal to beta particle. And the symbol of beta particle is like this. And we know that in electron, what we have 1 electron. So that's why instead of proton number, I'm going to write -1 because it shows electron. And there is no neutron. And so that means there is no mass. So it will be -1 and 0. These symbols are very important. So for beta particle, our symbol will be like this, -1 and 0. That means it's equal to electron and there is no mass for beta particle. And the relative charge of beta particle is -1 because it's equal to electron. A low mass compared with alpha particles, and we will neglect that mass in questions, which is very small mass. And the speed of alpha particles, 0.9 times the speed of light. So that means the speed of beta particles are 9 times greater than the speed of alpha particles. So we can say that the speed of beta particles are greater than the speed of alpha particles. The next one, weak ionizing effect. So that means when they collide with an atom on their way, they are not going to easily remove electrons from the atoms that they collide. So they have weak ionizing effect. The next property, penetrating but stopped by a few millimeters of aluminum or other metal. So they can penetrate into the metals, but just by a few millimeters. And the last property, because of they are negatively charged, they can be deflected by magnetic and electric fields, like alpha particles. So these are the properties of beta particles. Now let's continue. The next one and last one is going to be gamma rays. So if we look at gamma rays, the particle of gamma rays, not particles, but electromagnetic waves and part of the electromagnetic spectrum. So the gamma rays are not particles. They are just electromagnetic waves. And they will be in what? They will be in electromagnetic waves spectrum. And they do not have charge, no mass, travel at the speed of the light, because of the gamma rays are electromagnetic waves. And we know that all electromagnetic waves travel at the speed of the light. And very weak ionizing effect. So they couldn't remove electrons from the atoms they collide. The next property, very strongly penetrating. So intensity reduced by lead and thick concrete, but never completely stopped. So they have very high penetrating level. They can penetrate into the lead and thick concrete. And they cannot be stopped, completely stopped. And because of the gamma rays have no charge, no mass, they are not going to be deflected by magnetic or electric fields. They'll just go through the fields without any deflection. So these are the properties of alpha, beta, and gamma radiation. Now let's go back to our main topic. So we have seen the properties of these radiations. Now we'll continue to main topic. Okay, now we will look at the beta decay in terms of quarks, how the beta decay happens in terms of quarks. So from GCSE, unstable nuclei emit alpha, beta, and gamma radiations. We have just seen the properties. Alpha, beta, and gamma radiations. Three main radiations we have for any unstable nuclei. And now we will look at the beta minus decay in detail. So let's see what is beta minus decay. A neutron in an unstable nucleus decays into proton, an electron, and electron antineutrino. So when we say beta minus decay, that means basically a neutron in an unstable nucleus changes into proton, electron, and electron antineutrino. So again, we have to memorize these equations. So these equations will be called as what? Beta minus decay. And when we say beta minus decay, a neutron changes into the proton, electron, and electron antineutrino. See how the nucleon number A, proton number Z, and mass are all conserved. So if we look at beta minus decay, we can easily see that the total nucleon number or mass number on the left side before arrow must be equal to the mass number on the right side after arrow. So let's check. Before arrow, if we look at the mass number, nucleon number, on the left side, the nucleon number is what? 1. So that 1 must be equal to the total nucleon number on the right side. So let's add them. 1 plus 0. That's all. So 1 plus 0, it will be 1. So 1 is equal to 1. So that means the nucleon number are equal on both sides. The same thing must be conserved for proton number. So if we look at the proton numbers, the proton number on the left side, before arrow, the proton number is equal to what? 0. So 0 must be equal to, if we look at the right side, 1 plus minus 1, it will be also 0. So that means the proton number are also conserved in beta minus decay. Now another beta decay, and we call that one beta plus decay. And in beta plus decay, a neutron in an unstable nucleus decays into proton, positron, and electron neutrino. So when we have beta plus decay, a proton changes into a neutron, electron, and electron neutrino. Again, the nucleon number, proton number, and mass are all conserved. And so it's what? It's beta plus decay. So when we have beta plus decay, so the proton changes into the neutron. Just reverse of beta minus. In beta minus, neutron changes into the proton, but in beta plus, proton changes into the neutron. So again, we have to memorize these equations for beta minus and for beta plus. If we look at beta minus again, so let's look at beta minus again. So if we look at beta minus, neutron changes into the proton plus electron antineutrino. But if you look at beta plus, proton changes into the neutron, just reverse of beta minus. And instead of electron, we have positron. And instead of electron antineutrino, we have electron neutrino. So these are different elements. We should be careful, and we have to memorize these reactions for beta minus and for beta plus decay. So now the beta minus decay in terms of quarks. So if we look at beta minus decay in terms of quarks, we said beta minus decay is basically a neutron changes into the proton, we said. And if we look at the quarks in neutron we have what? We have up, down, and down quark. And in proton, we have up, up, down quark. So that means basically in beta minus decay, a down quark changes into the up quark. Okay, the charge on the left hand side is -1/3. If we look at the charge, the total charge before arrow, we know that the charge of down quark is what? -1/3. And after arrow, it must be the same, like on the left side. The total charge must be -1/3. So let's check. If we look at the right side of the equation, after arrow, the charge of up quark is what? +2/3. And the charge of electron, -1. And charge of neutrino, no charge. So -1/3 is equal to, if we add 2/3 and plus -1, it will be equal to what? So -1/3 is equal to 2 minus 3 minus 1. -1 divided by 3. So that means the charges are also conserved. Okay, the charge on the left-hand side is -1/3, and the total charge on the right-hand side is 2/3 plus -1. Again, it will be -1/3 electron. So decay equation is balanced in terms of charge. So in beta minus decay, we can basically say that one down quark changes into up quark. So that is beta minus decay. Let's continue. The next one, beta plus decay in terms of quarks. And we have seen that in beta plus decay, a proton basically changes into neutron. And what we have in proton we have up, up, and down quark. And in neutron, what we have? Up, down, and down quark. And we can easily see that up quark changes into what? Down quark in beta plus decay. So one up quark will change into a down quark. And the total charge on the both sides of the equation is +2/3. As expected, the charge has been conserved in this decay too. And we can just prove that one. If we look at the total charge on the left side before arrow, we know that the charge of up quark is what? +2/3. And if we look at left side, the charge of down quark is -1/3, plus the charge of positron is +1, and 2/3 is equal to 1 minus 1/3. If you calculate that part, it will be what? It will be again 2/3. So 2/3 equals 2/3. So that means the charges are also conserved in beta plus decay. So we have seen beta minus and beta plus in terms of quarks. Let's continue. Okay, now we'll look at types of radiations in more detail. So what are the three types of radiation? So we have just seen that we have three types of radiation as alpha, beta, and gamma radiations. So the radiation is emitted from unstable atomic nuclei, the first discovered by Henry Becquerel by accident. And we have three types of radiation: alpha, beta, and gamma radiations. So the easy as A, B, C. We have just said it and say again. Alpha radiation. Alpha radiation is basically a helium nucleus. It has 2 protons, 2 neutrons, and a charge of +2, where E is the elementary charge. And beta radiation, the fast moving electrons, beta minus or positrons, beta plus. And the charge of beta radiation could be -1 or +1, depends on the beta minus or beta plus. And gamma radiation, we said the gamma radiations are not particles, they are basically electromagnetic waves, or we can say high energy photons, no charge, and they travel at the speed of light. Now let's see the effect of electric magnetic fields on charges. So we can distinguish between these 3 particles by their deflection as they move through an electric or magnetic field. We said alpha and beta particles will be deflected by electric and magnetic fields because these particles, alpha and beta, are positively and negatively charged. But gamma radiation are not going to be deflected by magnetic or electric field because they do not have any charge. So let's look at 3 different of radiations and how they move in electric field. So if we look at the electric field, so we have the positive plate at the top and negative plate at the bottom. And when the 3 types of radiation, alpha, beta, and gamma, pass through the electric field, they will be deflected in these 3 different ways. Alpha particles will deflect downward, the beta particles will deflect upward, and the gamma particles will not deflect it because they are neutral. So how can we decide the direction of deflection? It's very easy. We know that in static electricity, like charges repel, unlike charges attract one another. So when we have positive charge at the top, and we know that the beta particles are what? The beta particles are negatively charged. So positive, negative. So the negative beta particles will be attracted to positive plate. So that's why they will be deflected in this way. Unlike charges attract one another. So what about the gamma rays? We know that gamma rays are positively charged, and we have positive plate at the top, and we know that like charges repel each other. So positive plate is going to repel positive alpha rays downward. So that's why they will be deflected in this way. It's very easy. And the gamma rays, because of the gamma rays are neutral, they are not going to be deflected. They'll just pass straight like this. So it's a deflection of alpha, beta, and gamma rays in an electric field. So let's continue. And if you look at here, the magnitude of deflection, the higher mass alpha deflected less than the low mass beta. So if you look at the deflection, the alpha rays deflected less because they have higher mass. The higher mass will be deflected less. Why? Because of the Newton's second law. F is equal to mass times acceleration. So they will be deflected less because of the higher mass. And we will have similar effect in magnetic field. So if you look at a strong magnetic field, the similar deflections are seen when traveling through the magnetic fields. Fleming's left-hand rule will show the direction of deflection. Don't worry about Fleming's left-hand rule because we haven't studied yet. When we study, we will be able to find the direction of deflections, alpha, beta, and gamma deflections. Now, the next one is absorption. Alpha, beta, and gamma radiation are ionizing. So that means they can remove electrons from the atoms. They cause ions to be formed when the radiation collides with matter particles. Alpha particles are very positively charged, so they interact with ionized matter very easily. Beta particles are less charged, so can travel further. And finally, gamma rays are the least ionizing and travel furthest. So we have seen this property before. So we said the alpha particles can be stopped by a paper, or they can just travel a few centimeters in air. And beta particles are going to be able to pass through paper, but will be stopped by a few millimeters of aluminum. And finally, gamma rays, they can pass through paper, aluminum, and in lead, they couldn't be completely stopped, but just a small portion of gamma rays will be able to pass through very thick lead. So these are the penetration levels of alpha, beta, and gamma rays. So the experiments with radiation. Ionizing radiation can destroy or damage living cells. So it's an important property. Sometimes we will see these properties in questions. Ionizing radiation can destroy or damage living cells. We said the alpha particles have very strong ionizing effect. Beta particles weaker than alpha, and the gamma particles will have the least ionizing effect. So the radioactive material, radioactive sources are stored in lead-lined boxes for safety. So otherwise, they will be easily passed through the other materials. So that's why they have to be kept in lead-lined boxes. When using sources handled with long arm tongs to keep them as far from the body as possible. So while dealing with these particles, these radioactive elements, we have to keep them far from our body. Otherwise, our body will be affected by these radiations. And finally, take a background count first and subtract this from any measurement you make. So let's continue. Yeah, the next one is going to be, next title is nuclear decay. So in nuclear decay, the radioactive elements have unstable nuclei that decay. So that means they basically emit radiation. And we said we have three types of radiation: alpha, beta, and gamma. Whenever we have radioactive elements which are unstable, these elements will emit radiation. And the radiation will be in terms of alpha, beta, and gamma particles. The original unstable nucleus is the parent nucleus, which decays into the new nucleus called the daughter nucleus. So we will have the parent nucleus before the reaction, before emission, and after emission, we will have the daughter nucleus. And this process is called transmutation, okay? Whenever we have a radioactive decay, this process is called transmutation. And transmutation means a complete change from one form into another form. And in radioactive decay, the parent nucleus or parent element will change a complete new element, which is called the daughter nucleus. So the next title is conservation of mass number and atomic number. So when a nucleus decays its mass number and atomic number are reduced by the values of the radiation type. When a nucleus decays, its mass number and atomic number are reduced by the values of radiation type. And let's remember again, whenever we have an element, let's say the element X, so we have some symbols, and we show the atomic number by Z, and the mass number by what? By A. These are important symbols. The Z is going to be atomic number or proton number. Atomic number or proton number. And A is going to be what? A is going to be mass number. Okay, or we can say atomic mass. So when we have radiation, the daughter nuclei will have some less atomic number and less atomic mass. Depends on the types of radiation, and we will have examples how they will be affected. Okay, let's continue. So let's look at some examples. And the first example is alpha decay. Emitting an alpha particle, we said in alpha particle we have 2 proton and 2 neutron, causes nucleon number to reduce by 4 and atomic number by 2. So the element will have been transmuted. What element will radium-226 transmute into via alpha decay? So if we look at the radium-226, when it emits alpha particle, it will change into the radon. And if we look at the atomic number before the reaction, before the arrow, and atomic number after the arrow. So if we look at the atomic number on the left side, so it's what? It's 88. So this 88, the atomic number, total atomic number before arrow, must be equal to the sum of atomic numbers on the right side after arrow. So we have what? We have 86 plus 2. So that means 88 is equal to 88. Yeah, the atomic number is conserved. So we should we should have the same thing for atomic mass or mass number. If we look at the left side, we have what? We have 226 atomic mass on the left side must be equal to 222 plus 4. Yeah, so 226 is equal to 226. So it's balanced. So emitting an alpha particle causes the nucleon number to reduce by 4. So it was before the radiation, the nucleon number was 226, and after radiation, it will be 222. So that means reduced by 4, and atomic number will be decreased by 2. It was 88 before radiation, but after radiation, it became 86, reduced by 2. So it's an example for alpha decay. So let's continue. Now we will see beta decay. Nuclei can be unstable by having too many neutrons. One of them can decay into a proton, an electron antineutrino. The proton stays in the nucleus, and the electron antineutrino are emitted. The neutrino is uncharged and very nearly massless. It was proposed to account for the apparent low energy of the emitted electrons. So it was supposed to account for apparent low energy of emitted electrons. So they will balance the energy for the reaction, neutrino. So if you look at the beta decay of a neutron, we said in beta minus decay, a neutron changes into the proton. And we have what? We have electron and we have electron antineutrino released. If you look at it in symbols, emitting a beta minus particle causes the nucleon number to remain constant and the atomic number to increase by 1. Yeah, let's look at this reaction. So on the left side, we have SR, and the proton number of SR is what? 36. So 36 must be equal to the total proton number or atomic number before arrow must be equal to the sum of the proton number after arrow. So on the right side, we have what? 39 plus what we have? Minus 1. So that means 38 is equal to 38. These are balanced. So that means the atomic number after radiation is going to increase by 1. It was 38 before reaction. After reaction, it became 39. So it's the properties of beta minus decay. So next one. So the next one is beta plus decay. Emitting a beta plus particle causes nucleon number to remain constant and atomic number to decrease by 1. Yeah. So for beta plus decay, instead of electron, now we have positron on the right side. And if we look at the atomic number before radiation was 19. After radiation, it became 18. So it's been decreased by 1. So 19 is equal to 18 plus 1. So 19 is equal to 19. So it's balanced. Yeah, so it's beta plus decay. And finally, gamma decay. A nucleus with a surplus of energy following alpha or beta decay will emit photons in the gamma spectrum. The nucleus will not change following gamma emission. So whenever we have gamma emission, gamma decay, atomic number or mass number will not change. It will stay the same. So the before reaction, before radiation, the proton number, let's say Z. After radiation, it will be again Z. The mass number A. It will not change. It will just release energy in the form of electromagnetic waves. Now, let's do some past paper questions related to these reactions. These are very, very easy questions. So let's check. First one. Example, a uranium-235 nucleus absorbs a neutron and then splits into 2 nuclei. A possible nuclear reaction is given by, like this. And question A, state the constituent particles of uranium-235 nucleus. So that means basically in uranium-235, how many protons we have, how many neutrons we have. So we can easily find it. Just write it uranium-92 and what? 235. So we can say that the uranium has 92 protons. So the number of protons in uranium is equal to what? 92. What about number of neutrons? Number of neutrons in uranium will be what? 235 minus 92. So which is equal to, let's use calculator, 235 minus 92 is equal to 143. 143 what? Neutrons we have. That's all. state the constituent particles of the uranium-235. So we have 92 protons and 143 neutrons we have. So let's go to the question B. Complete the figure 7.1 for this reaction. So it's basically asking what is A, B, C, and D. It's also a very easy question. To find A, B, C, and D, we will use the conservation of proton number and conservation of atomic mass, atomic number. So if you look at the number of protons on the left side, I mean before arrow. So before arrow, we have these particles, but after arrow, we have these particles. So that means the total number of protons before arrow must be equal to the total number of protons after arrow. So on the left side, what we have 92 and B. So that means 92 plus B must be equal to, now I'm going to add the number of protons on the right side. What we have, 37 plus D plus what? B. But in front of a neutron, we have what? We have 2. So that means 2B should be. And we know that the question is saying that a uranium nucleus absorbs a neutron and then splits into 2 nuclei. So, and basically in neutron, we can symbolize the neutron like this. In neutron, what we have 0 proton, 1 neutron, and 1 atomic mass. The symbol of neutron is like this. So that means basically B is going to be what in this case? B is going to be 0 in this case. And again, if you look at right side, what we have on the right side, 2B. B is again 0. So cancel this and this. These are 0. So what's left? 92 is equal to 37 plus D. So from here, D is going to be equal to 92 minus 37. So which is equal to, let's use calculator, 92 minus 37 equals 55. So D is going to be 55. And what about C? I'll do the same thing for C. But for C now, I'm going to take mass number. So total mass number before arrow must be equal to total mass number after arrow. So before arrow, what we have 235 and A. So that means 235 plus A must be equal to what? On the right side, we have what? 93 plus C plus 2A. Actually, I know that A and A is what? Neutron. And neutron, this A is equal to what? 1. So that means instead of A, I can write 1. Here is 1. Here is 1. And the equation will be left side, 235 plus 1 will be 236 is equal to, on the right side, 93 plus 2 times 1, 2. 93 plus 2, 95 plus C. And from here, C is going to be equal to 236 minus 95. So which is equal to, let's use calculator, 236 minus 95 equals 141. 141. So that's all. We have found all values. So basically, A is going to be 1, B is going to be 0, C is going to be 141, and finally D is going to be 55. So we have found all values. So the question is going to be very simple, related to radioactive decays, and we should use just the conservation of the number of protons and conservation of the number of atomic mass. Yeah, so today we can just leave here. I think it's enough for today. The next lesson will continue to the same topic. We haven't finished the particle and nuclear physics, so we may continue next lesson. Yep, thank you and see you next time.